good to be back with you. Today I'm going to do a new video about an old topic. I'm going to talk about how to measure the mass moment of inertia of an object. Now, I did a video about this before and there's an error in it, and boy did I hear about it, and that's how it should be. So today I'm going to fix that. So if you were looking at the previous video and you found my error, I apologize. Oh, okay. So, remind me, what is mass moment of inertia? Well, there's a lot of ways to think about it, but you can think of mass moment of inertia as a resistance to angular acceleration. Okay? This is the equivalent to F equals ma. This is the rotational equivalent. Sum of the moments equals I alpha. Well, moments, we know what that is. That's moments acting on the body. That's rotational acceleration. That's mass moment of inertia. That's the rotational equivalent of mass. Okay? The more mass moment of inertia an object has, the harder it is to get it to rotate. You know, if I put my hands up here like this and try to rotate, it's easy. If I were to put giant pieces of metal in my hands, like dumbbells or something, and hold them out here, well, the mass moment of inertia went way up. Now I have to, it's much harder to get my upper part of my body to accelerate back and forth. That's mass moment of inertia. In your homework problems, typically when you're working with mass moment of inertia, it's an object that's pretty easy to calculate. It has a lot of bars and rings and plates and stuff like that in it. But there are a lot of objects that are much more difficult to model. Here's one. This is my ripstick. Okay, I ride this sometimes. It's nice to ride it around the building. I fall off it sometimes. That's okay too. How do you calculate the mass moment of inertia of this? This is a complicated shape. I don't think I know how to do that. There's a lot of shapes like this, and one of the ways people do this is to use something called a bifilar pendulum. And bifilar is just an expensive term for saying it has two strings on it. So if I hang, let's see, I'll hang this. If I hang this from two strings, twist it, and let it go, it'll sit there and rotate like this. It'll oscillate, okay, back and forth in a sinusoidal way. If I can figure out what the period is of that rotational oscillation, and I know the geometry of my pendulum, I can figure out the mass moment of inertia. Okay? So that's the big idea here. If I hang an object from two strings, there's one, there's the other, there's the other, and some fixed mount up here, the ceiling, or some bracket or a frame or something, and I have some object down here. If I take that object and I rotate it this way and let it go and let it oscillate back and forth, okay, I'll get a period. If I know what that period is and I know some geometry here, I can figure out the mass moment of inertia. So let's get the geometry down. All right, here's the deal. There's two ways to describe the distance between those two strings. One is to call that d, and the other is to divide it in half, and I'm going to call that b. There's 26 letters in the alphabet. I got to call it something. All right, so 2b equals d. Now, different derivations you'll find in books and online use either this or this. All right, I used this initially, and boy did I hear about it. So I'm going to do it both ways here. So that's the first thing you need to know. And the next thing you need to know is the length. Okay, now that's always L. I've never seen it be anything else. So what I'm going to do at this point, and oh, by the way, here's the expression in terms of B. This is I, and I'll tell you where this comes from here in a minute. Mass of the body being swung, acceleration of gravity, B squared T squared over 4 pi squared L. Okay, that's the expression. Now, if you want it in terms of D, you get mg d squared T squared, I think it's over 16. Okay, these are equivalent, it's just whether you write them in terms of B or D. So what I want to do now, two things. I'm going to do an experiment to actually measure the mass moment of inertia of an object. And the other thing I'm going to do is I'm going to derive these. I'm going to derive those first, and I'm going to do it right now. it's going to take a few minutes, so if you want to skip ahead to the experiment, go ahead, all right? If you believe I got these right, but some of the people have been writing in want to know where those come from. Let me get them out of your way here. Want to know where those come from, so that seems like a pretty good thing to do. I'm going to pause right here, and I'm going to derive those two. Then we'll do the experiment, okay? Whoa, looks like the derivation elf has been here. What I'm going to do now is show you how to derive that expression for I that uses the measured value of either frequency or period, depending on how you want to do it. If you're not interested in this part, that's fine. Just skip ahead to the experiment part that's going to follow this, okay? Now, if you want to stay along, here's what's going on. Here's what a bifilar pendulum looks like. The solid lines here are when the pendulum isn't displaced at all, and the dotted lines are when it is displaced. And there's really two angles that I'm interested in here. Alpha, which is the angle between the string before it's displaced and afterwards, and the other one is theta, which is the angle between the initial angle of the part that's being swung, okay, a bar in this case, and when it's been displaced. Now I want to be clear, there's a bunch of different ways to derive this. I looked around on the web and some books and things, and I didn't really find anything that was that complete that I liked, so I went ahead and did it for myself, and I got the right answer here. If you see other derivations that are a little bit different than this, probably a little cleaner than this, that's okay. They're going to get you the same place. This is just one way to do it. There's more than one path that'll get you from start to finish. So anyway, when you've got these two angles here, here's what the geometry looks like for the strings. There's that angle alpha right there, and this distance right here is b theta. Remember, the distance that an arc travels is r theta. Well, r in this case is b. In fact, I can even write it down here if you want. Okay, that's b, and so is that. If that helps, maybe we'll use that. Now, as I said, you can use b or you can use the entire distance. I'll show you both of them here in a little bit. So anyway, that distance is b theta, that length traveled. Right, now one of the things we're going to use a lot here is something called the small angle approximation. Try this on your calculator or whatever your favorite computational device is. Set it to radians. Now this only works in radians. Look at sine alpha and alpha. Plot one against the other if you want, or maybe look at a table. As alpha gets smaller and smaller and smaller, the sine alpha is approximately alpha. So if you say sine of 0.01 radians, what you're going to get is about 0.01. So if the angles are small, sine alpha turns into alpha and tangent alpha turns into alpha, and just for completeness, cosine alpha turns into 1. What this does is this makes it so that some of these nonlinear terms here go away, right? This only works if you're only swinging through a small angle, okay? Couple of degrees, right? It does not work, the expression I'm going to derive for you does not work if you have like a 45-degree angle on the bifilar pendulum. It's just a very small deformation or displacement. So anyway, if you look at this in the geometry, and this is this triangle right there, right? B theta over L, where the L is that distance right there, that's the length of your string, is equal to sine theta. Well, if angles are small, then B theta over L equals theta, right? This is an approximation. But at small angles, it's a very good approximation. It's not a major source of error for what we're going to do. And you see stuff like this in derivations all the time, because leaving those in, those trigonometric terms, makes the math much, much more complex. It makes it much harder to get a usable result, actionable result. Okay, using similar triangles, what do the forces look like? There's what the string looks like. What forces are at play? If this is the force that's in the string, the tension in the string, well, the vertical component of it is Fy, and the horizontal component is Fx. I care about Fy because that's going to be, for each one of those, half the weight of the bar, because I've got two strings. So Fy on one bar is going to be half the weight of the bar, and Fy on the other bar is going to be half the weight of the bar. This is the horizontal component. This is what makes it want to go back and forth. So I really care about these two quite a lot. Well, that's the one I care about the most right now, okay, because that's going to what generates the moment that makes the bar go back and forth. So I can write Fx equals Fy tangent theta, because that divided by that is tangent of theta. Well, if the angle is small, if alpha is small, I can replace that tangent theta with theta, okay? And the other thing I can replace is that component and that component are almost the same thing if the angle is small. So I'm going to replace that with mg over 2. So that's the mass of the bar times the acceleration of gravity over 2. This is half the weight of the bar, if you want to think about it that way. So I'm starting to run out of board here. The horizontal force is, okay, mg over 2 times alpha. Well, I know what alpha is. It's over here, all right, if the angle is small. So that's what I get. Okay, there it is right there. That's the expression for the horizontal force. Well, I need the moment, not the force. Well, the moment is just the force times this distance b. So there it is right there. And by the way, that negative is very important. That's because as I move in one direction, the force is in the other direction. There's going to be another minus sign here in a minute that needs to cancel out, and that's really important. So if I take that expression right there and plug it in for f right there, that's what you get. Okay? And that's starting to look an awful lot like the expression I wrote down earlier. So that's the first part of the expression here. Let me do the second part. I'm just going to erase some of this. And I will leave that because we're going to need that here in a second. Okay? And we don't need that anymore. Okay. All right. So here's the deal. In order to write out our equation, it's really called an equation of motion if you're into vibrations and dynamics and stuff. The sum of the moments equals I times alpha, which is I theta double dot, okay, where theta is the angle of the bar. That's what we're going for here. Well, I know what the moment is. It's twice that. So the sum of the moments are minus mg b squared theta over L. Let me make sure I'm doing this right. I've got my cheat sheet right here, so let me make sure I'm doing this right. I've messed up once before. I don't want to do it again. So that's the sum of the moments equals I times theta double dot. So there you go. I want the other marker. That's an equation of motion. It's a differential equation of motion, actually. Okay, well, all right. I got double derivative there, curvature, if you want to think of it that way, and this other stuff over here. What am I going to do? Well, one of the things you can do, and one of the things you'll see your professors do a lot, is I'm going to assume that's sinusoidal motion. It is. Okay, so what I'm going to write is that theta is just some amplitude, whatever that is, e to the I omega t, right? That's what sinusoidal motion looks like if you write it out in complex terms, complex exponential terms. Well, the nice thing about this is it's really easy to take derivatives. So all I got to do is I get I omega a e to the I omega t, and theta double dot is minus omega squared, because I times I is minus 1, a e to the I omega t. All right, well, let's plug that into here. Okay, so I get minus mg b squared over L. I'm going to plug that in right there. A e I omega t equals I. There. Now I've got this minus omega squared term, a e to the I omega t. All right? I haven't changed anything. As long as that's really truly sinusoidal motion, I haven't changed anything. Well, we know from experience that it is. The nice part, that cancels out and that cancels out. Okay? I'm almost there. You can see I'm ready to bring it home here. Last thing you need to know is omega equals 2 pi times frequency. I think that was one of the mistakes I made earlier, so apologize for that, gang. Another way I can do this is I can say it's also equal to 2 pi over t, because frequency is 1 over t. Now remember, this is in hertz. Frequency is in hertz. That's in radians per second. That's why the 2 pi is there. So let's see. If that's omega, omega squared is going to be 4 pi squared f squared, and that equals 4 pi squared over t squared. And you can see where we're headed here. I'm going to go back up here to write the final equation out, just because it's... Do I have room? Yeah, I guess I got room. Let's do it this way. So let's plug this into that. All right? So my negatives are going to cancel out there, so I get mg b squared over L. Okay, now I got I, and I've got this omega squared there, so 4 pi squared over t squared. Okay, all I got to do is push that stuff over to the other side and I'm done. So let's do that here. Alrighty, so here we go. Right, let's bring it on home here. So I got m, whoops, that was terrible. Try this one more time. mg, so there's that, b squared over, or times t squared. Okay, and that's over 4 pi squared. That equals I. Okay, I'm going to double check it against my sheet here and make sure I'm not lying to you. And, oops, I forgot the L. Hang on. There's the L. Okay, now I got it. See, always check your answer. So there you go. There's the expression I had before. The one thing people were writing to me about or making comments about was what happens if I don't use that B. If I say the distance between the two strings is D, and that's 2B, well, all right. I can say, I'll get out of my head out of your way here in a second. Okay, what I was doing with that is, if that's D, okay, that distance is D rather than 2B like I had in the derivation, I'll just throw that in there. Then I can also say mg d squared t squared. Now I've got a 4 squared in the denominator here. So it's 16 pi squared L equals I. There's the other way to write it. Okay, and that you pick whichever one you want. Okay, so those are both correct. Alrighty, so hope that helps. And at this point, let's do an experiment. Alright, now here's an experiment I've set up in my office. I've got a solid bar of aluminum suspended just right above the floor, and I've suspended on 2 parallel strings. This is just cotton line, and you can see here I've got the lines fixed to the ceiling there, real high tech. I used binder clips on the suspended ceiling. So there's one and there's the other one, and those 2 strings are parallel to one another. Now let me put this down here, and let's see if I can do this. There we go. Now you can see actually move it up a little further. Now you can see the bar right there. And let me show you the 2 tests I'm going to do. The first, I'm going to very carefully move the bar and let it go back and forth there as a pendulum, as a regular simple pendulum. And I'm going to count the period as it moves. So a period would be, for instance, from there to there. Now typically what I'll do is I'll measure 10 of them, count to 10, and divide the total time by 10 to average out any errors. Okay, so there's the first measurement we'll make. The second measurement we'll make, I got to get this to quit moving. There. The second measurement I'll make is to twist it here and let it move. Now I don't have that quite right because there's a lateral superimposed. Let me try this again. Now if I do this right, if I keep the center of gravity over that little mark on the floor, there we go. See, I've got rotational motion with hardly any translational motion. And again, I'll count, or I'll time the period. So a period might go from there to there. And again, I'll time 10 periods and then divide them. Now remember, when you time a period, it's best not to start start timing right when you let go. You ought to let it go through a swing and start on the second swing. So let me show you. If I were to take this, go like that. All right, go. 1, 2, 3, and so on. Now, of course, the more you count, the less error you'll have. For if you're a carefully run experiment, about 10 is enough. Okay, let's bring it on home here. The experimental data is in hand now. Let's see if we got the right answer. Okay, see if it makes sense. So when we did this, when I did the simple pendulum, I got a period of 3.12 seconds. That means when I went out and back, right, it was actually 31.2 seconds for 10 swings, so that's 3.12 seconds. Now the frequency of a pendulum is a square root of g over L, and this is in radians per second. So a radian is 2 pi times the frequency in hertz, or 2 pi over t, where t is the period. That's this. We know the period, we measured it. So back out g out of this and write that. Well, why? Okay, the idea here is we know g, it's 9.81 meters per second squared. Now we've set up an experiment. That experiment better be able to duplicate a known answer before we trust it to do something we don't know. So it better be able to duplicate this. It better give us g without us having to use g in this side of the equation. We didn't. Measured that. That I did with a tape measure, basically. All the experimental data is over here. Okay, the mass of the bar, length of the string, which is what we're talking about there, all this other stuff. And by the way, there's the calculated mass moment of inertia using the expression that's in all the textbooks. We should get pretty close to that. Okay, so plug all these numbers into this expression here, and by substituting an omega you get there, and you get to here, 9.81, and it's actually 9.810 something, so it's really pretty good. All right, so this is great. This is correct. So we know we've got a system that's giving us correct results. We can trust it now. So all we got to do now is go to the bifilar pendulum. Okay, and there t was 2.91 seconds. Close, but not exactly the same. And again, it was actually 21 or 29.1 seconds for 10 swings. So that's where that number came from. Well, the expression that's, and this is I, I'll put EST there for estimated. This is our estimation of I. It should match that. Okay, it's mass of the bar, okay, times G times B squared T squared over 4 pi squared L. Okay, so I've got that over here. It's 801 grams. G is 9.81 meters per second squared. B is half the distance between the strings. Now again, if you want to put a D in there and use the full distance, that 4 becomes a 16. That's fine. It works too. Okay, there's the measured period right there. 4 is just a number, pi is just a number, and L is right, where is it? There it is right there. That's the length of the string. All right, if you work all those numbers out, I'll put that there. If you work all those numbers out, you get 0.0550 kilogram meters squared. There. Well, does that match? Yeah, pretty close. That gives us, we're accurate to within 8 parts in 550. Well, considering that I was hanging cotton string off the ceiling of my office to do this experiment, I'd say that's pretty good. In a more carefully constructed experimental setup, probably get closer. But that's not bad. Considering all the approximations we got here, that ain't bad. So there you go. After all this real long video, folks, I know we've got laid out how to measure the mass moment of inertia, derived the equation that makes it work, did an experiment, and then examined the data, made some calculations, and we've got pretty good agreement. So there you have it. Correct this time. I hope this helped. I'll see you next time.